welcome to another WJEC A level physics question. This time it's question 5 from May 2019's Unit 1. It's a question about moments, but it's also about experimental techniques and such. So the question goes, Sam carries out an experiment to determine the mass of a metal block using the principle of moments. So we've first of all got to state the principle of moments. So we're going to start with the idea that the object wants to be in equilibrium. So for equilibrium, the resultant moment on an object about any point must be 0. In other words, we can say that the sum of the clockwise moments equals the sum of the anti-clockwise moments. Don't necessarily need both statements there, but that's the general gist of the idea there. If we take moments about any point acting on this object, if that object's in equilibrium, there'll be no resultant moment because the sum of the clockwise moments is balanced by the sum of the anti-clockwise moments. In part B, the metal block is in the form of a cuboid as shown in diagram 1, and when setting up the experiment, Sam accidentally knocks the metal block so that it tilts to the position shown in diagram 2, and the block then returns to its upright position in diagram 1. So I've added a few lines to the diagram, sort of joining opposite corners of this block, and where those lines cross, well, that will be the centre of gravity of the object, and here we can see that that centre of gravity is just above the base. So let's start with that. So what happens there is that the weight of this object will cause an anti-clockwise moment. That will cause the block to return to the upright. If the block had been tilted any further, then that centre of gravity would now be past the base, and that would cause a clockwise moment which would cause the thing to topple. In the next part of the question, Sam sets up the experiment, and there's a diagram showing the apparatus here. This is 980 millimeters, the length of that part of the meter ruler, if you like. Okay, so Sam uses the Newton meter to measure the force F needed to make the ruler horizontal for varying values of D, and he carries out the experiment twice and determines a mean value of F for each of the distances D. And Sam judges that the ruler is horizontal by I before taking readings for F, and his results are recorded in the table. And we've got to complete the table for the mean. So mean, obviously, add the two values and divide by 2. So we get 2.7 for the first reading. With the second one, 5.2 plus 5.7 is 10.9, and half of that is 10.45, but we shouldn't give a mean to more figures than could have been read by the meter, so the 10.45 should be rounded to 10.5. Similarly, the 8.8 and the 8.5, that will give 8.65, but we're going to call that 8.7. Sorry, I've written 10.5 there, that should be 5.5. 1 second. The 11.2 and the 11.6 is 11.4, that's nice and easy. The 14.6 and the 14.5 would be 14.55, which again rounds to 14.6. And the 17.2 and the 17.6 rounds to 17.4. Next, the following relationship is used to find the weight of the block, WB, and by taking moments about the pivot show how this relationship is obtained. So, taking moments about the pivot, we've got two clockwise moments. We've got the unknown weight WB at a distance of D. And also we've got WR, which is going to be bang in the middle of the ruler, which, if we think about it carefully, is going to be it's 490 millimeters away from the pivot there because of this 10 millimeter bit at the end, and that's labelled as WR. I'll leave this in millimeters because millimeter conversions will cancel. So those are the two clockwise moments. The anti-clockwise moment is F at a distance of 980 millimeters. Now here, L, the 900 millimeters is L. So let's rewrite that slightly. So if the 900 millimeters is L, 490 millimeters is half of L. Just going to rearrange for F. So dividing both sides by L, we're going to get WBD over L here, plus WR over 2 here, because the two L's would cancel. Next, we had to plot a graph of the mean force against distance. I've already pre-plotted that graph. I've chosen a scale across in 100 millimeter steps and vertically going up in 2 Newton steps. We plot the points, draw a line of best fit, making sure that we're careful with a vertical scale. Each square on a vertical scale, remember, is worth a 0.2, not a 0.1. Now we're going to use the graph to determine WB, the weight of the metal block. Well, let's go all the way back to this formula that we've derived here and compare this formula to the formula for a straight line graph, which is basically y equals mx plus c. X is the D, y is the F. So by comparison, we should hopefully be able to see that the gradient of the line M is WB over L, and the intercept on the y-axis is WR over 2. So the gradient is WB over L. And therefore WB will be the gradient times L. So the gradient I've added to the diagram. I've chosen to use as large a triangle as possible. 17.4 for 0.8. It will be our change in Y, and our change in X here is going to be 850 millimeters. So I've used as big a triangle as possible to try to minimize uncertainties when we take readings off the graph. So gradient is 17.4 minus 0.8 over 0.85. Need to work in meters here, and that will give us about 19 or 19.5. Units for that gradient would be newtons per meter, and therefore WB is going to be 19.5 times L, and if you remember, L was 980 millimeters or 0.98 meters. So that gives us that the weight of the block is 19 or 19.1 newtons. Similarly, to find the weight of the ruler, we can see that the intercept is WR over 2, and the intercept is about 0.8. So WR is going to be 0.8 times 2, about 1.6 newtons. For the next part of the question, the distances D were measured to a resolution of plus or minus 1 millimeter. We're going to use data from the table of results to show that the percentage uncertainty in the mean F is greater than the percentage uncertainty in D when D is 100 millimeters. Well, to find the percentage uncertainty in D, we're going to take its absolute uncertainty of 1 millimeter, divide it by the actual value of 100 millimeters, and multiply by 100 to turn it into a percentage, and that's clearly 1%. To find a percentage uncertainty in F, we're going to do the same sort of calculation. We go back to the table. We can see that the mean value of F at 100 millimeters was 2.7 newtons. The uncertainty, the absolute uncertainty in F will be half the range. 2.8 take away 2.6 is 0.2, and half that is 0.1. So the percentage uncertainty in F is going to be 0.1 over the mean of 2.7 and multiply by 100. That will give us 3.7%, which is an acceptable answer, or 4%, which is slightly better. Generally, we go for one significant figure for uncertainties, but two figures are allowable, no more than two significant figures. For the last part of the question, we're just going to suggest one change to the method which would improve the quality of Sam's measurements. Well, we can see that the absolute uncertainty in the force is the largest uncertainty here, so we need to improve the force. So what we're going to do is use a Newton meter with a greater precision. Well, more precision. In other words, a Newton meter that can measure perhaps to hundredths of a Newton instead of tenths of a Newton. Whenever we try to improve an experiment, always go for the thing with the biggest percentage uncertainties first. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.